capabilities enabled by quantum technologies. And okay, I take a slightly wider start and say, okay, quantum 1.0, that was essentially old technology for our standards. That was the development of quantum mechanics in the early 1900s, was the understanding of many-body quantum systems, the energy levels in conductors, semiconductors, which of course underpins all of our IT. So effectively, it has a massive, without that, we wouldn't have computers, we wouldn't have an internet. All of that is already quantum 1.0, and it has a massive economic impact. And that's, of course, why now people are saying, oh, quantum 2.0, the new quantum revolution, that must be important, because the first one is really doing much of our economy. So what is quantum 2.0? And I've done a very, very high-level, simple view that now, instead of many-body average quantum effects, we're looking at the more spooky effects, as some people might say, in having single-particle quantum effects and being able to manipulate them and use them, being like superposition of like a particle being in two states at once, illustrated by Schrödinger's cat being dead and alive at once, or the entanglement where you have that kind of superposition across two particles. So like if one cat is alive, the other is dead, or the other way around, and that can happen over distance. Harnessing that, that's effectively what quantum 2.0 is. So what does that mean? How spooky is that? And actually it's maybe not quite that spooky, because if you think about, okay, what are quantum states? Like if you take the electrons, like what you know from chemistry, like the orbitals around like electron probability being in the ground state, being in one excited state. If you actually superpose these two, so you create this superposition, which is quantum 2.0, how that looks like in the probability distribution is like an oscillating electron cloud, oscillating at the energy difference between the two quantum states. So it's actually not quite as spooky. It's in two states at once, but actually it just means you have a wiggling electron cloud here. And of course, you can use that electron cloud now to build a quantum clock. So you take that oscillating electron cloud around the atom, which is the frequency of it given always by nature, reproducible because it's just the energy levels, and use that to stabilize like your clock, essentially count it. And that is already one of the quantum technologies. And these quantum clocks are old. This is the oldest quantum 2.0 technology, I would say, because they're around since 1967, where they define actually our time since then. So whenever you get a timing signal, that comes from a quantum clock. They underpin satellite navigation. You can actually, the point is about quantum sensors and timing, it's not in the future, it's here now. We're already using it. You can buy quantum magnetometers, you can buy quantum gravimeters commercially, early versions, but you can start buying them and using them. And many other quantum sensors are already proven in the lab to be better than anything classical. So sensors and timing are actually already now at the level where they can compete and where we need to think about how to make use of them. Just coming back to the satellite navigation, actually quantum 2.0 for this time, quantum clocks power our satellite navigation systems, which means they help us navigate cars, they help us provide timing for the internet, for communications, which means they already have an impact of 5 to 10% of GDP. So they're already a massive economic factor. And this is just the beginning of quantum 2.0. I'm just saying this is similar. And that's one of the challenges you have with sensors. Whenever you have new sensors or new timing capabilities, it might have a disruptive impact on the economy. So if you look at historic examples like Nobel Prizes, like 1899 X-rays, nowadays in every hospital, in every airport scanner, industrial quality control, electron microscope, MRI, medical applications, research applications, aperture synthesis in radio astronomy, that was in the 50s, which is synthetic aperture radar, which is underpinning our airspace control. giant magnetoresistance became in the high-density hard drives, and the CCD, okay, it's not in our smartphones, but it more or less triggered the electronic imaging, which is the social media trillion-dollar industry. So we're talking about disrupt. These are not quantum sensors as such, but I'm just saying if you have a new way of sensing, you have a possible very large impact on the economy. The problem is, the value is in the application. The sensor, no one cares about the sensor. It doesn't have much economic value. So you need a different type of thinking to make it happen. If you want to harness that for the economy, you really need assistance thinking for that impact. And okay, which means we need to start, ready now, we need to start linking physics, engineering, and industry in a systems way. Some themes quantum technologies can contribute to, which are also on the government agenda, is of course healthcare, particularly for the elderly, energy, how do we make the energy transition, mobility, novel forms of mobility, and the digitalization. So if we look at healthcare, it's already happening. We have, in the UK, there's a startup Circa, which does quantum magnetoencephalography systems, which you can buy, install in a hospital, and start taking pictures, which are of a quality higher than you can get with the squid-based systems, or the same quality, but now you can move. Which might go into things like having new diagnostic for Alzheimer's, which again is a $1 trillion impact on the global economy. Envision has just won a prize, and they have just spoken here, like a Baden-Württemberg startup, taking essentially spin manipulation based on quantum technologies to create a fast cancer treatment diagnostics, which will save, in some instances, like double 10% percentages of lives in some cancer cases. So really impact on the, and QN starting to do like controlling of prosthesis. So you start to have like real medical impact. And I see most of this sits on magnetic sensors. So this is my guesswork, a roadmap. Oil and mineral exploration, this has happened in the past. You always had atomic magnetometers, which based on these quantum superposition principles to look for like underground, detect oil and minerals. Quantum magnetoencephalography, that's the spin-off, which Circa, which is starting to happen now, still in the research stages. The next thing will be, of course, get FDA approval, do the clinical trials, make it an approved application. At some point, we'll have routine clinical diagnostics based on these quantum sensors, which will open completely different ways of looking into like brain function. And of course, once you understand that, you might go to a new type of brain-machine interface, being able to, like, without connection, to link. And of course, that's something the startup from Bosch is looking into with NV sensors. And of course, once you do that, maybe gaming will be the largest market in the end. Who knows? But also, like microsample chemical analysis, this is going in a similar direction as what Envision is doing, like analyzing or manipulating like chemical samples. Battery diagnostics, looking into the formation process of the like insulation layers inside batteries, looking at the formation of whiskers which might short them. How can we use batteries for electric cars longer? Like, no, they're still safe. How can we get them formed quicker? How can we make them more efficient? Magnetic sensors might open a big role here, but we need definitely the systems thinking, and we need the applied sciences to come in and start doing that research. What I'm saying, actually, I'm a quantum physicist. I'm saying don't give us all the money. Give it to the applied people who want to use the sensors for something else. What we're doing at DLR is also what's coming up, looking into applications for mobility. There is going to be a call later this year, QC Mobility, where we're working together with like several other DLR institutes to look at applications of quantum algorithms in like essentially in traffic, like air, street, ships, intermodal traffic. This will be a call for industry to get 100% funding to look into these problems, see if quantum algorithms can, like the problem can be adopted to, you can adopt a quantum algorithm to that problem, to test if the quantum algorithm is actually better than the classical one, has advantages. And okay, at the moment we can only implement toy problems on the existing quantum computers, but at least demonstrate that in principle it works. So keep your eyes open on the QCI website. This call is going to come soon. But also what we're doing for mobility, yes, we are developing clocks in the Institute, which are aimed to go onto the next generation satellites for Galileo, hopefully, so that we can have an improved clock there. But also we're looking into like navigation on ground by using optomechanical, like sort of 3 by 3 centimeter type, very sensitive inertial sensors or atometrophometry sensors for short and long haul inertial sensing, inertial navigation applications. That will still take some time to like develop. That's one of the more challenging tasks, but hopefully we will be able to navigate also in environments where GNSS is not available. Coming back to the clocks, if we have the clocks already since 1967, why should I be interested? There's a new twist to it in like what's now the quantum technology drive. Like the old clock, you just took your atom, you looked at it with a microwave, you stabilized the quartz onto the microwave, and then you read out the quartz with a frequency counter. The new way is to use an optical transition in the atom, so like a larger energy spacing between the levels, so that that oscillates at the frequency of light. So you stabilize a laser to it with the 2005 Nobel Prize of frequency comb translation from like Ted Hensch in Munich. You can convert that to a microwave, and then you can count it as well and use it like as a 10 megahertz sine or 1 pulse per second, whatever industry you need. Why is that interesting? The interesting is the optical transition is 100 times higher frequency than the microwave transition, which is you synchronize much, much faster, so you can synchronize clocks very quickly and to a higher precision. What's disruptive about it is this could be 100 times more sensitive or better than you can do with satellite timing at the moment. Many of our systems on Earth, communication systems, are limited or starting to become limited by what you can get as time from space. This will allow you to overcome these limits. And they also have lower noise than quartz oscillators. I'll show you some examples of that just to make a bit of advertisement. Like DLR has, like our clock at the moment is still at the forefront, but this is a JRC from the Joint Research Center report looking into what possibilities are there for next generation chip scale atomic clock. Can you make a clock which is chip scale, like just cigarette size, box large, and still has a primary frequency standard accuracy and the 10 to minus 15, 10 to minus 16 level. And so really like sort of 50 cubic centimeter, 250 milliwatts type, what DARPA, the US, are putting hundreds of millions into that. There's a lot of US activity, some in China, one in Germany, which is the DLR clock. And why should you be interested? Like, of course, we are interested for next generation GNSS, but we're also interested in like long distance 3D imaging radar. I'll say a few words about that, but with clocks you can start to synchronize to radar systems and get essentially really distributed sensing, like synthetic aperture on ground, which allows you to like see things very precisely. You can get the noise down, so you might get a means to do urban airspace control. Once you have flying like drones to deliver your packets, you want to know where they are in the city, and very hard to image with current oscillators. And of course, who knows where internet will go if we have 100 times better timing. I come to the autonomous vehicles as well. Like our interest is a bit in the space regulations. There's a lot of movement in the EU now. We have to do space traffic management. And of course, one thing you might do, if you actually have two satellite systems, okay, I'm back. Good. So if you have two radar systems and synchronize them to a fraction, like 1% of the wavelengths, which with these clocks you might be able to do even with 100 gigahertz radar, at which point, if you put these 100 kilometer apart, you see millimeter level resolution in space. And you can start to analyze satellites for what they're doing, can analyze space debris. So that's really exciting. That's where we are heading, hopefully. But if you use like these quantum clocks, they also have a lower phase noise. Sorry, this is a bit technical, but if you take radar, you essentially you send out a radio frequency pulse, you look at the back reflection, and you distinguish like the back reflection of a moving small object you're interested in from the back reflection of all the environment. by the Doppler shift, by the frequency shift. So you look at like signal power over frequency shift. And of course, if your oscillator has noise, you have a certain width to your back reflected signal from all the background. And if it's a city, you have a large, large peak of main back, feedback. This is an image from University of Birmingham, I should say, where I've been working before. But you get a large peak, and then the noise drops off over time, like this yellow line with a classical oscillator, and you're still able to see a plane there, which is a big signal moving very fast. But you might not see a bird, you might not see a small drone, maybe a helicopter. If you go for a quantum oscillator, like these optical oscillators, you can push the phase noise down, and you start to see all these things in an urban environment even. And so in Birmingham, like in the Quantum Hub, has been some trials looking at, like, these are still radars with a standard oscillator and a better, not quantum oscillator. But if you look at this drone like this, the not so good oscillator just sees the main body. The better oscillator, you start to see structure. You can start to see what is this, and that has an impact because you can start to distinguish, is this, like, what type of drone is it? Like a rotary one, a fixed wing one, or is it a bird? You can start to distinguish what's flying there. But also, like here, the yellow line is the better oscillator, the purple line is the more noisy oscillator. If you track a drone, like the trace is more or less the yellow line, but the not so good oscillator is losing it a lot, and this is not the most built up environment. So if you really want to have drone delivery in cities where there's lots of large buildings, you might need a quantum oscillator to actually track them properly. One last remark for like why maybe hundreds of millions are flowing into these clocks is like cloud robotics. If you want to have like the computation power for your autonomous car, for your drone, for your robots in an industry factory, if you want to have that computation power not inside the robot, but in a cloud, which is much more efficient because you can then use the computation power all the time, you need time-synchronized networks. You need to have a determined response time. And people IEEE is now looking into dead nets, time-sensitive networking, and trying to do, like the current internet standard has no time prioritization. So you might have like a few milliseconds, but you might have a 600 millisecond peak in the daytime. A millisecond in a car gives you a few centimeters. A few 100 milliseconds, you're in the wall. So it's a few meters. So you can't afford that. So you need some millisecond latency time data transfer. You can do that in principle in fixed, like ground networks, but it's really difficult, and there's no technical solution yet to do that with wireless networks. And so, because you also need to know where is the certain drone or like the robot you're looking for. The next generation clocks might help you with that. So if they really become chip scale and only €1,000 per piece, that might be really disruptive to realize that. And okay, overall, we're looking at quantum technologies for digitalization. Security, of course, we can do quantum communication. There will be also new applications like cloud quantum computing. There are quantum clouds coming up. How do you compute there without people knowing what you're calculating? And quantum authentication. Sorry, I didn't translate that in English. The deterministic thing I just said, by having time, knowledge of the time and position of your receiver, but also there's a lot of like new sensors to make these networks smart. With that, I'll finish. Like the Institute for Quantum Technologies in Ulm has these 4 divisions looking into like the clocks, optomechanical inertial sensors, photon sources, and an analysis of materials. I won't go through all that. I'm just saying there is a small stand there for the materials, and we are also on the Quantum Computing Initiative booth. So if you want to talk to people about these things, please come visit us. With that, I'll stop. Did I stay in time? Oh, I was quick. Thank you. Good. Any questions? Yeah. Oh, sorry.
So now you have these oscillations in this atomic clock. So how do you deal with the relativistic effect when you compare it with this stable Earth, right? Now this is moving very fast in a satellite. So how do you deal with this relativistic effect and how
you will need to add corrections. In the GNSS satellites, you already have relativistic corrections. And there's an interesting question, how good do you want the clock to be? Like if you take the very best clocks at the moment, 10 to minus 18, 10 to minus 19, that's probably not what you want to put on a moving platform, because like 1 millimeter in height is 1 part in 10 to minus 19. Just general relativistic redshift due to gravity. The Doppler shifts or the second order Zeeman effects will be huge as well. So probably 10 to minus 16 is where you want to go, where you are just like 2 orders of magnitude better than what you're doing now, but not as sensitive. Like to a meter level, you can probably trace where you are, and then it depends on the application. But it's definitely a consideration that at some point it doesn't make sense to get any better. Or you're measuring something else then. Any other questions? Okay. If not, then thank you again, and I'll stick around for some discussions if you wish. Yeah, thank you.